Welcome back to week 8 and your part 2 of your screencast for the last study lesson on Apex. And we are on 10.3.3, Half-Life, and we'll pick up where we left off, and it's talking a little bit more about carbon dating. So you've heard, with fossils and trying to figure out the age of different things, we use carbon dating for a lot of that, and we call it's a form of radioactive dating. And so that what it does is that carbon-12 is the most common isotope that we have. 6 protons, 6 neutrons, very common for carbon. And that is why on the periodic table, carbon, has 12.0, something like 1 or whatever, because it is the most common one. However, there is carbon-14. It's far less common, and it is radioactive. It does break down, and it has a half-life of 5,730 years. So what we can do, that we can track how much is left in a fossilized item, and then you can figure out how old it is. So we have this, it decays and it turns into nitrogen 14 through beta decay. Remember, it adds a proton, turns into nitrogen, which is number 7 on the periodic table, where carbon is number 6. And so we have that, and so the atmosphere always has about the same ratio, and we can kind of track what's going on. So it works because carbon-14 decays and carbon-12 doesn't. So when plants grow, they absorb the carbon dioxide from the air. They eat the plants, get the carbon, and most of the carbon is carbon-12, and then we have some carbon-14. So the ratio between these two isotopes, between carbon-14 and carbon-12, is the same ratio found in the atmosphere, as long as the plants keep growing and animals keep eating. But once the animal dies, the ratio is going to change. It's going to decrease. Okay, because you're going to have a smaller number on top, because the carbon-12 is not radioactive, won't break down, but the carbon-14 will. So less carbon-14 as the animal dies, and then we have a lower ratio. Okay, so the radioactive dating is done by observing the change in the ratio of isotopes. Okay, when it dies, it stops taking in any new carbon atoms through carbon dioxide or different things, and so it can continue to decay radioactively until it breaks down completely. It's not much less, and too small to kind of measure. And so we have this ratio of isotopes. This is the picture of something like a accelerator mass spectrometer, so used to kind of detect how much carbon-14 is in there. So they're going to have us kind of pick up the order of what's going on, so the events of carbon dating. So the first thing that kind of happens is that we have cosmic radiation happening in the atmosphere that's, colliding with nitrogen in the atmosphere. Then we're going to have this nitrogen-14 converting it to carbon-14. And then what's going to happen is plants absorb this from the atmosphere. The animals then eat the plants. Okay. Well, the organism is going to die eventually. And then we're going to have the ratio change at the end. So let's check it. Yep, correct. Okay. So with this, we have the half-life of an element is used in radioactive and should be similar to the age of the fossil. So carbon dating is common for the age of bones, because we haven't really had, bones that are older than the 5,730 years, a lot of it. But the problem is, if we have something that's a few years old or older than 60,000 years old, you really aren't going to get, an accurate measurement. So luckily, with other radioactive elements, we can find that we can use them to track to see how much is going on. So using this link, we're going to look, and I'll pull it up in a second, which element would be useful if we have a fossil that's over 1 billion years old. So if I look here, kind of look at my options, kind of go for the ones that maybe has a half-life around that number that's looking. So potassium, is that one of my options? Good. Potassium is there. Correct. Okay. Now with this, we've learned before that when radioactive elements decay, their number of protons changes, and it causes it to change into a different element. And so then once uranium, for example, breaks down and goes to the thorium, well, that'll also can sometimes be a radioactive element, and that'll decay as well. So the cycle will happen for a very long time. And as you look, their half-lives are different as well. And so we can kind of track what's going on. And you don't never have to memorize this chain, and it's not really, something that we can, but it is a reference of knowing that this is kind of the breakdown of uranium all the way down to lead, where it'll stop and it'll be stable. Okay? So we have its basis for one of the most accurate forms of radioactive dating is what we call uranium-lead dating, going from uranium down to lead, and then it kind of stops. It's stable. So let's review a bit of these. So to use uranium dating, which would a scientist want to measure? We're going to measure the ratio. Whenever you're talking about dating something, you're measuring the ratio of the uranium to the lead to get that. Now, which of the following would be useful for measuring? You don't want something that's hundreds of years. You don't want that's something that's 30,000 years, because you could do that for carbon, but the ages of old is wrong. Okay. The last few down here. So we have a lot of these things, and the safety or danger of radioactive material. We've kind of heard that radioactive material is bad or dangerous, but we use it for a variety of different things, and often in medicine. So in the field of medical imaging, an X-ray, almost, they're used to take pictures of bones, and so something we need a bone scan, we use iodine-131 is injected into the body, where the area of the bones that are cracked, and it'll give off radiation when it's decaying. Now, a camera can detect these waves as placed over this, and the method would pick up, the revealing bone damage that a regular X-ray wouldn't pick up. Now, the half-life of this iodine is only 8 days, so we can kind of see that's why as it's decaying, it'll give off this radioactive. And so only a small amount is used, and it disappears really quickly, but having a lot of it would be a bad amount. So we do use it. It is useful for its radioactive elements. Now, nuclear power plants, the big thing with this is that you do use radioactive materials to generate electricity. However, the biggest problem is the waste that's left over. The waste that's left over, once it breaks down, it lasts so long where it's still, radioactive. It's still breaking down, and so they have to store it in a safe place where no, radiation level, and it's always a risk of earthquake or disaster because they're burying it in different areas, and it's kind of a big problem that's going on, and one of the negatives of radioactive or nuclear energy. So anyway, plutonium is one waste product of it. It has a half-life of about 24,000 years. So we have not seen, we have not lived 24,000 years to see kind of the effects of this nuclear waste. But anyway, so if you have 1 kilogram of plutonium, how long does it take for half of the plutonium to decay? Well, half-life is 24,000 years. So it's done. Okay. If you have 1 gram of plutonium, how long will it be until you only have 0.25? Well, after 1 half-life, it's 0.5 kilograms. So after 2 half-lives, it would be 0.25. So 2 half-lives, each of them is 24,000, so 48. And then the last question, if you start with 1,000 grams of plutonium, how long will it be until you have less than 50? Well, if I think, okay, 1 half-life would be 500 grams, 2 half-lives would be 250 grams, 3 half-lives would be like 125, 4 half-lives would be like 75-ish, and we still haven't gotten there, so it's more than the 4 that's there, okay? So, okay. Now this about kind of ends this last little bit of half-life that's going on. So good luck on the quiz. If you have any questions, please reach out.